And this is super exciting. I hope you're ready. The derivatives that we've been finding for the last week or so all had fairly long processes where we had to use that difference quotient or the slope formula and take the limit and all those things. Great news. There's faster ways of doing it. Hopefully you kind of assumed there was a faster way because nobody can do the AP test with that all the time. So we're about to start our shortcut methods, and I hope you're as excited as I am. So very first rule, constant rule, just differentiating the constant function. If you think about the constant function, the slope of that everywhere is 0, so it should be no surprise that the derivative of a constant is 0. So our little example here, the derivative, remember d over dx means find the derivative. Finding the derivative of 23, just 0, because that's a constant, and derivatives of all constants are 0. So it's like the easiest one ever. The next one helps us deal with these power rules, and none of us, even though we really love the binomial theorem and Pascal's triangle, nobody wants to take anything to the 6th power, or much less the 13th over there, so we have a power rule. Let's see what the power rule says. Power rule says we take the power n down front and decrease the power by 1. That's sort of weird and cool all at the same time, right? So our first example here, find dy dx. Remember, that's just a derivative for, a notation for derivative. Our rule, power rule, says 6 comes down front, x decrease the power by 1. Done. So much faster than the binomial theorem and expansions, right? Okay, you find the derivative of f of x. Pause the video for a second and see if you match mine. Okay, we're back. Did you get 13x to the 12th? I hope so. Super fast, super easy, right? And check that out. No work to show. You just do it. What about these two? I gave you a power rule and a constant rule, and we don't have either thing going on. But wait, can we write the 4th root of x as a power? Yeah, we certainly can. So y equals x to the 1/4 power. Now the 4th root is written as a power, and we can differentiate it just the same way using our power rule. So dy dx, derivative of that, same rule. Bring the 1/4 down front, power down front, variable decrease the power by 1. What's 1 minus 1, or 1/4 minus 1? We would have a negative 3/4. Okay, and you can totally leave negative exponents in AP Calculus. It's a thing. So g of x, 1 over x to the 7th. Again, that's not written as a power function, so we should rewrite it. We're going to rewrite that as g of x equals what, class? Negative 7 power. Perfect. Now differentiate using the same rules before. G prime, check out that notation. When it's just the function, no g prime, don't forget. And now I'm differentiating, so I have g prime. Power down front, negative 7. X, decrease the power by 1. What's negative 7 minus 1? Negative 8. Fun, fast, awesome, right? Okay, let's talk about a couple more rules because they're just as easy. So a constant multiple rule. So we're talking about powers, x to the 3rd that has a constant multiple in front, like that very first one you see, 4x cubed. Okay, constant multiple rule, that's what we're talking about. So we get constant multiple rule. Maybe you guessed it. You just leave 4 and differentiate the power function part of it. So alternatively, we have this rule over here that says you can bring the power down front, multiply it by the coefficient. Both work just fine. They say the same thing in different ways, really. So dy dx over here, 3 comes down front, multiplies by 4, and decrease the power by 1, so 12x squared. Easy peasy, right? Sweet. F of x over here on the right, we better rewrite it first. So I'm going to say 5x to the negative 7th instead, so I can use my power rule. F prime going to be negative 35, sorry, x to the negative 8th. Awesome. Okay, notice that I'm using different notations. I do have a favorite. I won't tell you what it is yet, but this notation and this notation, one of them was favored by Newton, one of them was favored by Leibniz. They both mean derivative. We just have to get used to seeing both of them. Okay? One more rule. Sum and difference rules. So based on our examples here, we're going to be talking about how do we add and subtract all of these different powers and constant functions. This rule just says you find the derivatives of each little piece and add or subtract them. So derivative dy over dx is derivative of 3x squared is, 6x. Derivative of 5x, well, that's a power of 1. So we bring the 1 down front and we get 5x to the 0, and of course x to the 0 is just 1. And the derivative of negative 8 there, 0, because it's a constant. So our derivative is just 6x plus 5. The f of t function over here, we probably want to rewrite quickly because I see a variable in the denominator. So I'm going to rewrite this one quick as minus 3t to the negative 2. Okay, some people totally able to do that in their head. I'd rather you write it down just to avoid silly little mistakes. So the first one, 20t cubed. Next one is plus 6t to the negative 3 plus 2, and that negative 9's derivative is 0. So we just have this as our derivative. How you feel about that? Really easy, right? Oh, I hope you said yes. Okay, 2 last things. Find the equation of the tangent line to the function at a given point. And we had a worksheet question like this last week, and it was a bonus point on your quiz. So 2 things that we always need for the equation of a line. We need a slope, and we need a point. Sometimes people think we have to have the y-intercept. Not true. You can use a slope at any old point because we know point-slope form, and that's super awesome. So slope, how do we find slope in calculus? You find the derivative and then plug in the x value. So we have g of x, we're going to find g prime of x, 2x plus 3, and then we specifically need the slope at the point 1, where x is 1. So I need g prime of 1. So 2 times 1 plus 3 sounds like a slope of 5. So the equation of my tangent line, here's x, here's y, technically x1, y1, and this is my slope over here. So equation of the tangent line through that point will be y minus a negative 1 is equal to 5 times x minus 1, and no need to change that into any other form. Leave it in point slope form and move on. All right, here's a super fun thing at the bottom. Find the first, second, and third derivatives. Oh goodness, doesn't that sound like a great time? Of the following functions. Truly, it is super easy. So let's find first derivatives. We already know how to do those. So our first function y, first derivative is dy over dx. 4x cubed minus 6x plus 1. Okay, second derivative just means you find the derivative of the derivative. So here's some funky notation for you. Second derivative is d2y over dx squared. Okay, those 2's indicate it's a second derivative. And we just pretend like 4x cubed minus 6x plus 1 is a function, and we differentiate it following our rules. So that would be 12x squared minus 6. And then, what do you think for the third derivative there? We're going to have d3y over dx cubed. You just read that as third derivative. You don't read it like I just did. And we differentiate 12x squared minus 6. So we would have 24x. Super fast, super fun. So let's talk about first derivative of our function f over here. Okay, we got some pretty big exponents, but you're smart. We can do this. First derivative, 18x to the 17th minus 6x to the 5th minus 12x squared plus 14x. Okay, probably going to need a calculator out very soon, unless you're really good at mental math. Second derivative, I'll continue using this notation. We do f double prime for second derivative. And now I need 18 times 17. So 306 x to the 16th minus 30x to the 4th minus 24x. I ran out of room, plus 14. Okay. And our third derivative, we just keep on differentiating. Here's the notation for third derivative. It gets 3 primes, so f triple prime. 306 times 16, 4,896. X to the 15th minus 120x cubed minus 24. And that's our third derivative over there, because the derivative of 14, 0. I hope this helps you find some derivatives very quickly, and I hope it's even a little bit more fun.